This is another simple question on spring mass systems. So we have the question as follows. A spring of constant K equal to 100 Newton per meter hangs at its natural length from a fixed stand a mass of 3 kg is hung from the end of the spring and slowly achieves equilibrium position So this is the case of a vertical spring. A mass is hanging from a vertical spring and it achieves a new equilibrium position. So the question asks us to find the value of the quantity x as shown in the figure. So the figure is simply there's a ceiling, a spring is there and a mass is hanging from it. So x is nothing but this value, the new equilibrium position, wherein the natural length of the spring would have been just this much. So x is basically the extension in the spring to achieve equilibrium position when the mass is hanging from it. Then this quantity is x naught. Then the question says there are multiple parts to this question. The spring is now pulled down an additional distance x and released from rest. In such a situation, we need to find what is the potential energy in the spring after it has been moved downwards by a distance x. So after this equilibrium position, so this is the equilibrium, after the equilibrium further x displacement is given. The next part is, what is the speed of the mass as it passes the equilibrium position how high above the point of release will the mass rise? Since this is going to lead to simple harmonic motion, so the mass will oscillate up and down. So we need to find out the highest point. The next part is, what is the period of oscillation? So let us look at the solution to this problem now. So this is a pretty much simple problem. We have a vertically suspended spring, a mass attached to it. It attains an equilibrium position, and then we displace it by a distance x, and then we need to find out these quantities. So let us start with the first part. So in the first part, we need to find out the equilibrium distance. So if we draw the free body diagram of the mass, we have mg acting downwards and the restoring force acting upwards. So in equilibrium, we have, in equilibrium, since the net force is 0, everything is stationary. So for equilibrium case, we have mg minus fr equal to 0, which implies mg equal to fr. Fr is nothing but k times x naught from Hooke's law. Hooke's law says that restoring force is minus k times the displacement. So this negative sign basically says that the restoring force acts in a direction opposite to that of displacement, and that we have taken care of by drawing this vector in the opposite sign to the displacement. So displacement is downwards, the restoring force is acting upwards. So apart from the negative sign, which just shows the direction, the magnitude is going to be spring constant times the displacement. So spring constant times the displacement, and direction we have taken care of by drawing the vector upwards. So if we rearrange, we solve for x naught. X naught is nothing but mg by k. So this is the solution to the first problem. We can plug in the values. So we have been given that mass is 3 kg. So mg by k would be 3 kg into 9.8 meter per second squared over k is nothing but given as 100 Newton per meter, and we can approximate g to be roughly 10 meter per second squared to make our calculations easy. So 3 into 10 divided by 100 meters. So this comes out to be equal to 0.3 meters. So this is the solution to the first part of the problem. Now we will proceed further to the second part. Second part wants us to find out the potential energy in the spring when this block is potential energy of this entire spring mass system when this block is displaced downwards by a distance x. So the potential energy is given as half kx squared. So potential energy in the spring, stored in the spring, is half k times the square of the displacement. Now we need to find out this potential energy So knowing how much displacement we are giving and the spring constant, we can find out this potential energy from this formula. Next part asks the speed as it passes through the equilibrium position. So we need to note, let us draw the diagram once again. So if this was the equilibrium position, this was the natural length, this is natural length, this is equilibrium position, and this is the displacement x given from the equilibrium position. So we are pulling the block downwards and then releasing it. So speed at this point is 0. So speed at this point is 0. We are pulling it down, we are holding it, and then we are releasing it. So it starts with 0 speed out here, and the the potential. So if speed is 0, this implies kinetic energy is 0 because kinetic energy is proportional to the velocity squared, but the potential energy over here is maximum. Okay, so we have pulled it downwards by a certain distance. Potential energy over here is the maximum because this is the amplitude of oscillation that we will have. Then what will happen is, after releasing, the block would rise upwards. The block is going to rise upwards up to its equilibrium position. So at this point the potential energy is minimum, it is 0 because this is the equilibrium position. So at this point the potential energy is minimum, which we can set it to be equal to 0. Remember that potential energy is with respect to some reference, so we can always choose our 0 point of the potential energy. In this case, we would like to choose the equilibrium position as the 0 point of the potential energy. Otherwise, this could also be equal to half k x naught squared, because if we set the natural length to be as the 0 point of the potential energy, natural length of the spring, then up to equilibrium this distance is x naught. So if we set this natural length position as 0 point of potential energy, then we will have the equilibrium position at half k x naught squared. But for simplicity, we can choose equilibrium position as the 0 point of the potential energy, then we will have this condition over here. So if potential energy is minimum, then from conservation of energy, we have kinetic energy is going to be maximum, because total energy needs to be conserved. This comes from conservation of energy, which says that total energy is equal to potential energy plus kinetic energy, which is conserved. So this is from the law of conservation of energy. So that means the speed when the block passes through the equilibrium position is going to be its maximum speed. So let us now solve this. So we have the maximum potential energy at this point. So this is the maximum potential energy. This is basically this x displacement that we have given to the block is basically the amplitude of oscillations. So we can rewrite this as follows. This is nothing but the amplitude of the oscillations. So we can write it as follows. This is the maximum potential energy. And then we need to find out the maximum kinetic energy. Now from the law of conservation of energy, this has to be equal to the maximum potential energy. Why? Because if we look at the two situations, one is equilibrium and one is at the amplitude, then we see that in equilibrium the total energy is nothing but potential energy, maximum value of the potential energy, because kinetic energy is 0, and at the amplitude, sorry, I wrote the opposite. At the amplitude it is the following, and at the equilibrium position it is maximum of kinetic energy from here. So at equilibrium potential energy is 0, at amplitude kinetic energy is 0. So we have at amplitude total energy is nothing but just the potential energy, and at equilibrium total energy is nothing but the kinetic energy. So from here we get the following, and this comes from conservation of energy. So now we can solve for the maximum kinetic energy or the maximum velocity, or the velocity at which the block passes the equilibrium position. So we have this gives us the velocity as so knowing the value of the amplitude, we will come to know the value of the velocity. The next part, part D, wants us to find out the highest point after we release the mass. So since this is simple harmonic motion, the amplitude of oscillation would be the highest point. So for part B, the highest point so the block will rise a distance of A above the equilibrium position. Since this is simple harmonic motion about the equilibrium position. This is by definition of SHM. So if we know the amplitude of oscillation, we will know how high above the equilibrium position will the block rise. The last part is to find the time period of oscillation. So time period is, we have seen in previous videos, it's 2 pi square root m by k, and we are given these values. So plugging in the values, 2 pi square root 3 kilogram is the mass, 3 kg, and k is 100 Newton per meter. So plugging in these values in the calculator, we get roughly 1.1 seconds. So this solves this problem. This was a simple problem with multiple parts dealing with the energy aspects of the spring mass system as well. So potential energy and kinetic energy. So the important takeaway from this question is this expression for potential energy, and then we can use conservation of energy to find out the velocity in this particular situation. So this solves this question.